welcome everyone to the last keeping current of the semester, a strange semester for us all. Well, we've all heard of Vesuvius in Pompeii, but how many of us have heard of Herculaneum? Only people who've been keeping abreast of the Herculaneum Project. And so today we have Christy Chapman, Stephen Parsons, Seth Parker, and perhaps Brent as well, Brent Seales, talking about that project, which has been going on for a while. And it's always good to get an update as to what's up right now. So take it away, folks.
Well, in lieu of our fearless leader, who I don't see has connected yet, suppose I will do a brief introduction. So yes, we are formally known as the ADUCE Lab. The ADUCE moniker goes back a long time within our research group. It originally stood for the Enhanced Digital Unwrapping and Conservation of, I actually can't remember the last E, but it was an elaborate acronym that Dr. Seales came up with, essentially around this concept of digital unwrapping of texts that are hidden inside damaged objects. And so for a long time, at least a decade, I've been a part of the project now. For a long time, we've been focused on this problem of how can we recover text from inside badly damaged manuscripts, damaged so badly that you can't physically open them. And we rely on a number of technologies to do that. But also we've sort of expanded beyond that scope of just virtual unwrapping and digital unwrapping. We've actually started to explore what digital conservation and digital restoration means for digital humanists, and explore new technologies and ways that we can bring our computer science, computer vision, and computer graphics abilities to the realm of the digital humanities so that we can enhance the scholarly output that digital humanists are coming out with for badly damaged texts. We originally were going to be following a schedule of a presentation where each of us was going to present a number of slides and switch back and forth between sharing those slides. I believe I was the first one in that rota. So I'll go ahead and share my screen here. So what we're going to try to introduce you to today is just a number of the different technologies and different approaches that we've been working on. And it involves both imaging and machine learning, and most importantly, out of all of this, the metadata surrounding all of those processes. Because we're trying to build a holistic view of what it means to work within the digital humanities on sort of intelligent three-dimensional objects, intelligent in quotes because I just needed a word for it, I suppose. So I've been focusing within the last year largely on the problem of photogrammetry. And just as some background, this that you're seeing in front of you is a Herculaneum scroll. It is not one of the more commonly known closed Herculaneum scrolls that we've spent so much time trying to sort of digitally open. This is actually a scroll that was physically unwrapped. It's called PHERC-118, and it's held at the, as you can see in the copyright there, it's held at the Bodleian Library in Oxford, United Kingdom. And this scroll was physically unwrapped, and then sort of the pieces were pasted down onto boards. And there are 12 boards exactly like, that look very similar to this, that represent all of the physical pieces of this scroll that have been unwrapped. It's sort of difficult to tell from just this photograph, but there is actually text visible on this surface. And for over 100 years, scholars who want to read something from Herculaneum have traveled to the Bodleian Library, they've traveled to Paris, France, or they've traveled to Naples, Italy, and they've looked at trays just like this, and they've painstakingly looked through microscopes at the characters that are sort of visible on the surface, and they've created readings of the text based off of what they see under the microscope. But as you can tell from just this photograph, there's not a lot of contrast there. I mean, this is a very large tray. This is something, actually, I believe this particular tray was large enough that they put it in a frame and originally hung it up on a wall. They don't do that anymore, thankfully. But this, this is a fairly large item that you would feel comfortable hanging on your wall as sort of a beautiful piece to show off to all of your friends. But you can't see anything on the surface of this scroll, just sort of naturally. So as digital imaging came along, and as, in particular, spectral imaging gained popularity within the realm of digital imaging, we were able then to start using things like infrared photography to improve our reading of these texts. So now what you're seeing is an image of the same scroll from 950 nanometers infrared. And now you can actually start to see lines of text, in particular down here in the bottom and up here. And if at full resolution, you can actually start to make out characters, readable characters, Greek characters on the surface of this scroll. And this is great. I mean, these, for the last 2 decades, probably, we've had images of Herculaneum scrolls, open Herculaneum scrolls that look like this, where we can actually start to see the text more clearly. We can make readings that are not as confounded by this sort of contrast issue. But this instead in particular shows a major problem with these open Herculaneum scrolls, which is these are still 3-dimensional objects. Even though we physically opened them and flattened them, quote unquote, there's a lot of surface undulation. There's also places where layers were stuck together when the scroll was physically open. And you can't actually tell where one layer begins and another layer ends just from a photograph. You lose that depth that sort of shows you the step edge between 2 layers that have been stuck together and sort of broken apart. So that's sort of information that a scholar could see if they were working with the material in person, in Naples, for instance, but they can't see very well in the photograph. And so this is the sort of information that we've been focused on trying to bring to the scholar through digital forms. And in particular, we've been trying to do that through sort of 3D acquisition of the surface structure of these scrolls. So previous work in 2016, we went to the Bodleian Library and we imaged this set of 12 trays to capture their 3D surface structure. Now, some of our work with the intact scrolls sort of showed us that laser scanning these surfaces is extremely difficult. The laser scatters very easily or absorbs very easily. It's a little unclear, but it's very hard to use a laser to sort of capture fine detail surface structure. So instead, we focused on sort of visual imaging techniques, things like photogrammetry or structure from motion, where we can sort of enhance the photograph that's captured to sort of show us the fine details. It makes the image noisier, but we can actually, bump up the gain of the image and see the fine details of the structure, and then use that to reconstruct the surface. So in 2016, we did sort of a test pilot with 1 tray, and then we went back and did all trays in 2017 using the system you see in front of you. This is an Artec Space Spider, and it's a handheld structure for motion system, not structure for motion, sorry, structured light system that is, you just sort of wave over. It's like handheld. You can see how large it is. It's like an iron you'd use to iron your shirts. And you just sort of wave it in front of the object that you're trying to scan, and it would continuously capture the 3D surface of the object you're looking at. And you can see on the computer screen there in the back, the surface model being constructed sort of in real time. And this worked fairly well for these scrolls. This is a complete reconstruction of this scroll. At the same time in 2017 that we acquired the 3D, we also acquired a hyperspectral image cube. So where multispectral imaging, you may capture a photograph of the scroll under 10 or 12 discrete spectral bands. Here in hyperspectral imaging, you're capturing hundreds of spectral bands across the near visible light range, ultraviolet to infrared light range. And so here we're showing the infrared 950 nanometer wavelength image derived from that hyperspectral data set. And we've applied it on top of the 3D surface model that we captured of this open Herculaneum scroll. So you can now get the infrared aligned with the 3D surface structure. Now, the big problem, I mean, this is great. We love that we have this data and it looks great. But the problem is that there are thousands of scrolls that we would like to do this process to. And it took us, 3 or 4 days to do 12 trays of the 1,000. So, you can do the math on how long it would take at, 12 trays over 3 or 4 days to do thousands of them, right? It's just not feasible. So we wanted to look into a way in which we could automate this process, this 3D scanning process, so that we could go to scale and capture the thousands of scrolls that are at the Biblioteca Nazionale in Naples, Italy. We also wanted to shift to something that's we'll say a little bit more reproducible, a little bit more straightforward than structured light imaging. Structured light is very powerful, but requires quite a bit of pre-calibration to make sure that you sort of understand the scene and the pattern, the expected pattern of structured light that you're projecting over your scene. So we actually focused in our project on photogrammetry, which is completely unstructured sort of in its initial phase. This is gaining more and more popularity now, but so many of you may already be familiar with this technique. But essentially, you take photographs of a scene from multiple positions, and by tracking features within those images, you can solve for the camera positions, and in some cases, the camera intrinsics and things like that, that tell you where the cameras are within your 3D scene. And then you use that information to triangulate the features into a 3D model, a 3D point cloud. And you can project the photographic information that you have from a particular camera pose onto the triangles of your now triangulated mesh. And now you have a textured 3D mesh of your scene that's as high, the texture is as high resolution as the original photographs that captured the scene. So the key here is that you move the camera through the scene and take multiple photographs, and the differences in perspective, similar to how we see 3D in real life, the differences in perspective between those two poses tell you about the object structure that you're capturing. So just to make this a little bit more concrete about how this works, imagine that you've taken a photograph of this beautiful line of apples. There weren't many apples this year because of our late freeze in the spring, but imagine you've gone apple picking and you want to show them off on Instagram. If you take a photograph from where this left camera is of all of your apples in a line, you're only going to see one of those apples, only the one that's sort of directly in front of the camera, just by the nature of the way the perspective works. But if we move to a second view to the side and capture those apples from the side, well, now we can actually see in our right view, here's our 4 apples lined up in a row. Now, you may have noticed that we have this nice angle, known sort of correspondence between these two images. I can't see all of the apples here, but that actually tells me that all of the apples are in line with my camera. They're in this sort of center viewpoint line. But over here, I also have the lines, the rays projecting out from my camera to each apple. And if I know where these two camera positions are in 3D space, I can actually draw a line between them. And that actually creates a triangle by which I can now solve for the 3D positions of all of these apples using this information. In photogrammetry, this is essentially what photogrammetry does. It uses the structure within the scene in the process called structure from motion, uses the structure within the scene to figure out where the cameras are and then to triangulate the positions of features within that scene. The hard part, of course, is knowing where your cameras are. There are software packages now that help you figure that out with some degree of accuracy. So, but that's sort of, the software pipeline, the reconstruction pipeline. We still have this acquisition problem. So over the spring semester and into the summer, and actually last fall, now that I think about it, we've been working on building an automated photogrammetry scanner for these sort of flat object structures. And that is what you see here in front of you. This is a 5-camera system where we'll put our trays within that blue box there on the board. And then using this XY gantry, our 5 cameras will move across the surface and capture 5 pictures of every point of every position on the surface of the scrolls, open scrolls that we're looking at. Here's a close-up of that 5-camera array. This has now changed a little bit. We're actually been working on some improvements to the camera head, but this gives you the idea. We have these 5 FLIR cameras pointing straight down, or 1 straight down and 4 at an angle, so we can sort of capture each surface structure. And then here is a proxy tray sitting in place from directly above. This is actually something Stephen, who is on this presentation, he actually made this carbonized scroll that you see in front of you. And if you are interested, I'm sure he'd be happy to answer questions about how that was constructed. But he made a carbonized scroll, and we taped it down onto a board, and have been using that as sort of a proxy example. And there is actually text on that that should be illuminated through infrared light. If you look really close up, you can see just how flaky and fragile these surfaces are. This looks very extreme, and perhaps is in that it's a proxy, but it actually looks very similar to what the real trays, the state of the real trays in close-up can look like. It's extremely fragmentary, extremely fragile, and there's lots of fine detail there that we want to capture. This is a video of our system running. I'm not sure if that will play well for you all over the internet, but essentially our camera just moves a known pattern. Our camera head moves a known pattern over the surface. And so we know where all 5 of our cameras are when we capture the images, and we track that information and feed it into our photogrammetry system to sort of improve our 3D reconstruction. Here are some example images from those 5 cameras. You can see that within each view, this was all captured at one time step. The camera moved and captured these 5 images all at the same time. You can see the overlapping field of views within this, and this is sort of one example what we'd feed in. And here's another capture position of the same object, showing some of those fine detail features. And our capture times here are not actually very long. We're actually able to get enough light onto the surface that we can get this with very, I think we're maybe at a second capture time, and that's going to be improved as we add more light to the system. And one more capture position. So once we take this image data and we run it through a reconstruction pipeline, what you see on the right is the 3D reconstruction from the photogrammetry system of the tray on the left, using just our grayscale images from our camera head. And while that's all nice, they look the same. That's good. That's a good validation that they look the same from a distance. But what's really powerful is when you can sort of zoom in on the 3D model, and you can see that surface detail very close up. Maybe it will do it. Having some lag here, I think, from well, it's kind of hard to tell, but the fine detail is there. That's what we really are interested in, how that we get that fine detail so we can see those small step edges between surfaces. And we are actually capturing that. I believe that's another video, which I'll skip since we're having trouble with the playback. So that's what we've been working on with our photogrammetry system. We are sort of nearing completion of the design of that system. And we would expect, we were planning on being in Naples now if to do the imaging, but of course the pandemic has sort of upended those plans. So we're sort of looking ahead and trying to plot when we'll be able to go to Naples and image all of those thousands of trays. The photogrammetry system, if any of you are in the Marksbury building in the next couple of months, it is in the Marksbury building. You can send me an email if you'd like to see it and see it in operation. We're hoping that what we're able to provide the scholar through that whole photogrammetry process and the 3D models that we're producing will lead to better readings of the materials that the scholars already had access to. But that's just one component, right, is to provide that 3D surface structure. There is also this other component, which is improving the ability to actually see text on these surfaces. And so we also have a long line of sort of post-processing and research into how we can improve our ability to see text on both those open scrolls and our sort of intact Herculaneum scrolls. And that's what Stephen is going to talk about now, ink identification for Herculaneum. Stephen?
Sure. Thanks, Seth. I can't start my screen share until there you go. Yeah, so I'm going to be talking about one part of our efforts to do ink identification, and this is going to be about looking at texturing as multimodal imaging. And texturing in this context is one step of the virtual unwrapping pipeline. So I'll do a very brief overview of this. I'm sure many of you have seen this before. But this is the virtual unwrapping pipeline. On the left is a photograph of a scroll. Looks like a lump of charcoal, is a scroll. And when you put it in a CT scanner, you get a three-dimensional scan where you can see the interior. So that's pictured in the middle. This is sort of one slice or cross-section of that scroll. And then the unwrapping pipeline starts with segmentation. So the red curve in the middle is called a segmentation, or it is illustrating the process of segmenting one of these pages from the others. And you can see this red curve sort of follows one of these layers all the way around. And if you were to trace this curve all the way through the volume, we're only looking at one slice here, but if you did it for each slice in turn and looked at its shape in 3 dimensions, you get the next image over to the right, which is the shape of that layer or that wrap of this scroll in 3D. And this horizontal red line shows the process of texturing working its way up that mesh. So the top half of the mesh is essentially only 3-dimensional shape information. The bottom half has been textured, and after this process runs all the way up, we can then flatten the mesh and you can see the text more clearly, like the image on the far right. So this talk I'm going to focus on the texturing phase. Excuse me. And this is kind of a conceptual talk about what it means to texture something from tomography or from X-ray, and how we can sort of expand that definition, and hopefully it can allow us to see with not only a more powerful lens, but you can sort of change the lens you're using to look inside these scrolls. So texturing traditionally in our pipeline has looked like this. We just looked at this, but essentially what's happening is it's working its way along this mesh, and at any given point on the mesh, that's a point on some triangle deep inside the mesh, right? And what we want to do is go back to where that point came from inside the 3-dimensional volume and look at the local neighborhood and apply some function to that neighborhood that determines what color is sort of rendered at that point on the mesh. And if you apply it to every point in turn and you've picked the function correctly, you see useful information. So in this case, this is a fortunate case where the ink is iron gall ink, so it shows up more clearly, or it actually shows up brighter in X-ray than spots that don't have ink. Because the ink actually has iron in it, it's more dense, and it's sort of like looking at a bone in a hand X-ray versus the fleshy parts that aren't bone, right? The bone is brighter. So the ink does the same thing. So the function in this case can actually be quite simple. You can apply sort of a max operation or a mean or average operation to the local neighborhood and just sort of plot that value on the point, and it will be brighter where the ink is brighter. It's pretty straightforward. And the result is you can read it. So that's great. But you essentially get what is a modified view, an X-ray view of the surface. That's really good because you can see the text, but it might not be how you really would have loved to image this surface. If you had this scroll and you could physically unwrap it, if it wasn't damaged and could tolerate being opened, you would open it up and the scholar might want to image it. And would they choose X-ray if they had all of these other options? Maybe, but probably not, right? So one example of something they might choose instead, based on what we just saw from Seth's talk, is infrared imaging. If we could open this up in real life, we might want to look at the surface, especially of the Herculaneum scrolls, in infrared, because as Seth illustrated, the text actually shows up under infrared light, where it often doesn't to the naked eye. And there are many other examples of scrolls you would want to do this with. Another example is maybe you would want to image this in hyperspectral. So this is a palimpsest where depending on the spectral band we're looking at, you can see either the text on the top, or you can see the more faded text in a different orientation that's sort of the underlayer, or that maybe was there previously but then washed away before the new text was applied. Hyperspectral is really powerful, and also, as Seth mentioned, you can image across many different bands. You might have hundreds of different bands for one imaging. So instead of like an RGB photograph where you just have 3 values, you might have 270. Another option, though, having mentioned RGB, is just a color photograph. Maybe you actually do want a color photograph of the surface. For a lot of materials, many of them are damaged and require sort of special techniques like infrared to make the text show up clearly. But there are plenty of materials where that's not true. And they actually look good to the naked eye. So it's a shame that this thing is rolled up and we can't open it. But maybe if we could open it, it would look fine. Really what we want is just to take a color photograph of it. So maybe that's what you would have done. Or maybe you would use something like X-ray fluorescence. X-ray fluorescence is really powerful, and it gives you sort of an elemental breakdown or composition of different inks and things on the surface. So that's all great, but unfortunately, you can't do any of that when you have an intact scroll that's rolled up and you can't open. X-ray is the only thing that really penetrates enough to give you tomography to let you look inside it. So you're always going to get a sort of X-ray view on the left. But it'd be great if you could at least try to sort of mimic these other outputs. So it turns out one can do this, and this is sort of an illustration of that. We see 4 different rows here of our carbon phantom scroll, and the top one is a color photograph. And so we introduced neural networks to be able to identify carbon ink. And where I'm headed with this is that you can use neural networks to sort of mimic any of those modalities. But we originally introduced those to this problem not for that reason. It was because there were these cases where we couldn't see the ink at all. We weren't trying to look at it in a different light. We were just trying to see where there was writing. So the touch shows what this surface looks like when photographed in color. But if you roll it up and actually put it in the CT scanner and apply the virtual unwrapping pipeline, you get this second row, which is our traditional texturing. And you can see that these dots show up very clearly, and some of these numbers, like this 5 at the top of column 5, shows up quite clearly. Those are all written in iron gall ink by design. So those are great, but these large delta characters are written in carbon ink, which is practically invisible. So we used a neural network to sort of learn to be able to identify where there's carbon ink, and I'll show a bit more of how that works. I also presented some of that in the spring in this seminar, so I'm trying, I won't entirely go over all the details since you may have seen them before. But with the neural network, we can identify where there's ink, and that's wonderful. This is the best we've ever been able to see carbon ink. But then it also occurred to us, we can sort of skip this step of having to identify a binary label of ink or no ink. This requires some manual annotation. Someone has to open this top row in Photoshop and sort of trace out where there's carbon ink. And then we use that as input to the neural network. But we can actually skip that and just use the original photograph as input to the neural network and say, at any one of these points, the network needs to learn to reproduce what would that point look like in color. So can it learn to sort of reproduce a color image and generate that only from the tomography? And it actually does really well. And this bottom row is an example of that output. Now, the reason it can't perform well on this very first character is expected, and that's because the ink thickness is changing with the column here. So the first column has only 1 light application of ink, and the second has 2, and so on. So by the time we get to the 6th column, this is sort of an unusually strong or very thick layer of ink that's easily detected by the network. In the first column, the ink thickness, which we've measured with the scanning electron microscope, is actually smaller than sort of 1 voxel or 1 pixel in the 3-dimensional scan. So we would expect, since it's about 4 or 5 microns thick and the voxels are 12 microns each, that is sort of below the detectability threshold. And sure enough, that turns out to be true. But this would indicate that if you can scan this scroll at higher resolution, if you could scan it at around 4 or 5 or 6 microns, you would expect actually to be able to read the ink here in the first column, where we've never been able to do that before. So that will hopefully be the topic of a future talk, since UK is acquiring a new CT scanner that hopefully has that capability. but not quite yet, so maybe next time. But anyways, I wanted to talk about just this concept that we can learn to reproduce anything based on the tomography. And we hope this is going to be really powerful for us, and so far it has been. But we hope to apply this to many different methods. This is just another illustration of what we were just seeing with the learned RGB. So we have the color photograph here, and then kind of behind it faded out is the texture image generated, is sort of the output of running this whole scroll through the traditional virtual unwrapping pipeline. And a part of that pipeline is that, for any of these points on this surface, we know actually we have a layer of information here that is just a bunch of pointers to positions and normal vectors inside this three-dimensional space. So for this point, we know not only that it should be tan and should have this particular RGB representation, we also know it comes from this point in this volume. And so we can fetch just a little cube or the local neighborhood around it as the input to the network. And the output are these three values of red, green, blue. And we're essentially telling the network, here's a little cube of data. I'm telling you that the center of this cube, if we looked at it through a camera in visible wavelength, would look tan. So you need to be able to learn that pattern. And you feed it a bunch of examples and it learns it. So here's another point that might come from where there's ink, so it should look black. So that the network learns that pattern, and that's what we just saw. But actually the idea is that you could put anything here. Maybe you have scanned the surface not with photography or traditional photography, but maybe you've been able to subject it to scanning X-ray fluorescence. So for every pixel, you don't just have red, green, blue values. You might have its response across the whole X-ray spectrum, and which would give you a lot of information about what elements are present there and so on. Or maybe you've been able to image this scroll in infrared or in hyperspectral, where you have 270 different responses across the entire light spectrum. So the point is, you could use any of those as inputs to this network. RGB is arbitrary. So yeah, maybe you have 270 values, that's fine. You could plug that in as your label, and the network should be able to sort of learn the pattern and reproduce an image as if that were acquired in the first place. So this is just a detail on the architecture of this network. It's a pretty simple, at its core, three-dimensional convolutional neural network. So it just starts with this 34 by 34 by 34 three-dimensional subvolume is what we call it, but that's the same cube you just looked at. And as it goes through the network, it's convolved down quite small, and then there's a fully connected layer. And then the output here is the sort of binary ink or no ink. So we have two class output values here. But like I was just illustrating, instead of two, you could have anything here. In the RGB case, there are 3 numbers as the output, but you could put 270 there. We've implemented this in PyTorch, and we make use of UK's Center for Computational Sciences compute cluster to run these jobs, and we use the GPU servers. So that's been really wonderful over the last few years. They use the Slurm workload manager to schedule these. A lot of these training jobs take hours or days to run, so it's really nice. We can sort of schedule up a whole batch of them, and they run as the compute resources are available, and then we get the results as they're ready. And the source code for this project, which this was not true last time I talked about some of these stuff in this forum, but is now available on GitLab. So there's the link. I'll show it again at the end. And here's an example of applying this with just the RGB, but applying this to some new data that we haven't presented here before, which is from not the Herculaneum collection, but another one where the RGB works really well, actually. And this is called the Morgan M19 Manuscript. Now, this is just a fragment of it. This is a whole book or codex that we've imaged, but this is just one little piece that was imaged separately as training data to be able to hopefully apply this method to the rest of the book. The left is a photograph of the fragment. The middle is the sort of traditional texturing method, what that produces if we scan this and then run it through the pipeline. And the right is what we're able to produce using this method I've been talking about. So I'll just point out a few areas where that works better, we think, than the traditional method, because it's able to pick up on some subtleties that aren't really captured if you're just trying to express, bright spots are ink and dark spots are not ink. So there's some example of like a discoloration here that may or may not be ink. Actually, I'm not certain if this is ink or some damage to the surface. But in either case, if you were looking at the surface, you want to be able to see that. So it's not captured too well in the traditional method, but shows up pretty well with this new one, because the network sort of implicitly learns all of these things. The same is true here. There's sort of a faded or discolored area here that we can see on the right. It's true in a couple more spots, and the same is true on the character itself, where the ink actually shows up a lot clearer here. So the next steps of this are to apply it to the internal pages, which is the interesting part. The slide I just showed is applied to a fragment where, we have a photograph of that surface. We know what the text is on that surface. And so it's quite cool to be able to reproduce it from X-ray only, but not all that useful because someone could just go and actually take a picture of it because it's exposed. What we want to do is apply that where we can train on this fragment and then produce that color photograph of some of the internal pages of this manuscript, for which we don't actually have photographs, and we can't get photographs because you can't open up this book, it's too damaged. So we've started that process, and the network is actually able to generalize better than we're expecting. So we're starting to generate some of those images. None of them are quite ready for prime time, but that's been exciting. And then another one is to sort of extend this beyond RGB and actually give this a shot with some of the other modalities. So one of those will be acquiring some spectral images for some objects that we have tomography scans of. So we actually have a tiny little flake of Herculaneum scroll that we haven't yet been able to get infrared or spectral photographs of, but we're hoping soon to image that on our new spectral camera setup. And then we will run it through the pipeline and see if we can reproduce it. And a lot of people go into imaging all of these things and organizing these projects. So I'd like to acknowledge all of them, especially Christy, who I think you're about to hear from next. But this is me acknowledging that Christy does a ton for our team. She helps us run basically everything. So thanks.
Thank you, Stephen. So I'll share my screen. Okay, so today I am going to talk to you about metadata matters. Like Stephen said, I'm Christy Chapman. My role is the Research and Partnership Manager. And one of the aspects of that is being the translator between the technologists on our team and the rest of the real world. So you may be wondering why we're going to be talking about metadata, but I promise it is related to Stephen and Seth's talk, if you'll just hang with me till the end. This is the metadata universe. This is a map kind of all of the different standards that were out there back in 2010. It's complicated and messy, and we could spend a whole semester of very boring keeping current talks just discussing metadata, but we're not going to do that today. I'm just going to talk about some basic concepts and then why it's important to us and why it should be important to the computer scientists.
Christy, if I could, yeah, sorry, your presenter view is showing to us, not your slides.
Oh, well, is that better?
That's got it.
Yep. Okay, thank you. So first, what's the definition of metadata? A lot of people just want to call it data about data, but that's really too simplistic because it provides much more than that. It gives contextual information and understanding about any kind of object, whether it's digital, analog, text, image. And the early types of metadata, they actually go all the way back to the library in Alexandria, when librarians would put little hanging tags on the end of a scroll that basically serve the same function as the card catalog, which some of us in this call remember, where you would go to the library and try to find a book and pull out the card, and it would give you all of the details about the book you were looking for. It's not a representation, I mean, it's not the book itself, it's not the content itself, but it's information about the content or information about the object. And metadata has actually moved, out of the cataloging world into our world. Today, metadata looks like this. It's machine readable markup language so that the metadata and the tags can be searched and surfaced. And most of us are familiar with this type of metadata, where our camera, our iPhone camera, or whatever, a Google camera, Google phone, if we have that, automatically captures a lot of information without us doing anything. It's like magic. we take a picture and all of a sudden it tells us where we were, what time it was, what day it was, all of the settings. If we've been really organized and have attached names in our images, it will even tell us who is in the photo and pinpoint the exact location of where we were. So why does metadata matter, though, to the computer scientist? And the truth is that metadata actually makes good science. In 2016, a group of representatives from academia and industry, funding agencies, and scholarly publishers got together and designed a set of principles for the management and stewardship of scientific data. And what they have said is that scientific data must be fair. And basically what that means is scientific data must be findable, accessible, interoperable, and reusable. And of course, one of the keys to making data fair in this way is actually metadata. Because today, if you tag it, they will find it. But if you don't tag it, it doesn't really exist almost. It just kind of disappears into the digital ether. A lot of us have desktops that look like this, where there's all sorts of data that hopefully we've named in a nice way so that we can search and surface. But if we tag things well, it makes that process even better and more efficient. Fortunately, software does a lot of that for us, so we don't have to do it ourselves, but that is something that the software engineer, of course, has to include in their process when they're designing. Which brings me to sort of a different but related reason why metadata is important, and that has to do with trust. Besides metadata making data fair, metadata can engender trust in the data. This image here is from last year's episode of Nova, where they talked about the deep fake videos and the use of software tools that use spatial mapping and voice transfer, so that people can actually make fake videos now where someone appears to be actually saying something that they aren't saying. And obviously these can be used for nefarious purposes. And the truth is that a lot of what happens in computer applications for the average person really does seem like magic. I mean, you click a few buttons and all of a sudden whatever you need to happen happens. And with these newer technologies involving AI, you know, there becomes a real sort of crisis of trust between the public and the people who are creating the software behind the scenes. In this particular case, you know, how can I, as a user, believe that what I see is truly authentic? This quote is from a New York Times article that came out in 2018, and it was about Harvard and another university building some ethical courses into their computer science program. And the quote, the first two lines of the article said, "The medical profession has an ethic: first, do no harm. Silicon Valley has an ethos: build it first and ask for forgiveness later." I'm going to take a moment. I highly recommend this episode of Radiolab, where they talk about the deepfake videos, and it's actually 4 years old now. So the issues they raise in it have only gotten worse. But I'm going to play a brief clip from that, where the interviewer talks to a computer scientist who's been involved in the facial movement mapping. She's from works at Facebook and is at the University of Washington, and she's interested in telepresence, where you can you know, create basically a hologram of someone who is maybe living in another country, and yet they can be in your living room talking to you. So that's what she's interested in. But listen to her when they question her about her concerns about the nefarious use of technology. You should be able to hear this.
Okay, well, I'm asking, are you afraid of the power of this? And if not, why?
I'm just giving my, I don't know, I'm answering your questions, but I'm a technologist, I'm a computer scientist, so not really, because I know how to, and I know that because I know that this technology is reversible. I mean, there is not worried too much.
I don't think she really answers that question very well. And we certainly don't feel very confident in that she's given any thought really to what the nefarious or the méchant in French uses of the technology could be. So again, let's get back to the computer scientists and what this has to do with us. Well, as Seth and Stephen have showed you, we use a lot of behind-the-scenes computer processing to generate our images. This is the one of the Engedi scroll where we revealed text from within an object that could not be opened. No one could ever check and make sure that that it says what we say it says. And there are lots of other applications of AI that create these types of what would you call it, facsimiles, using data that can't really necessarily be confirmed. Here is an example of one that uses a neural network to copy an artist's style. So you could take a photograph, for example, and train a network, and it will render the photograph in the different, in an artistic style of a particular artist, like you see Van Gogh there on the bottom left. The truth is that the ethics of the computer scientists demand that they consider how their tools will be used and design protections against nefarious uses within their software. And there is an ethical framework for the computing profession. The New York Times writer got it wrong. There's the Pledge of the Computing Professional, where our students say this every year, promise to use their skills for the public good, recognize that their work affects people's lives, that they have responsibilities to society. There's the 10 Commandments of Computer Ethics from the Computer Ethics Institute, which requires computer scientists to think about the social consequences of what they are writing or the system they're designing, and to ensure that the computer and their tools are going to be used in ways that consider and respect their fellow humans. There's the Acm Code of Ethics, which I'm not going to go through all of this, but it's in the PowerPoint if someone wants to look at it. There's a lot of ethical framework for computer scientists. So when we design a tool such as Seth and Stephen's, we as a team are thinking about how can we engender the trust of our users that what they see is truly authentic and it really represents what we say it says. And we have decided that metadata helps us answer that question. And we call this part of our lab EDUCE data. Metadata is important to us and to you because it provides digital provenance. Tags in this context become like a trail of breadcrumbs. Any single element alone isn't going to be too helpful, but together they can lead us to the truth about a digital object. Here's an example. This isn't one of ours. This is one I pulled from a library, but this is an image, and we use something called METS as our container, as our metadata schema, and it allows us to include all of the information about these complex digital objects that we're building. Even though they're made up of many, many disparate parts and many different files and many different formats, we can use this to outline the way they are built and constructed. This example here, which again is not ours, but it shows where this object is from. This gives a lot of detail about the object itself, what it's called, what it is, a physical description. But then it also, this tool also allows us to give information about how the images were captured, who produced them, what type of camera was used. Down here at the bottom, you can see there's even, or you can include some information about change history. This goes back to the example Seth showed where he talked about how we create a 3D model of these opened Herculaneum papyri. And you can see this is a process flow chart that I put together where all of these green items are actually digital images and the purple boxes are actually computational processes. So all of these green things get fed through a purple box and out comes an image. And we have added a step that collects metadata and provides metadata in a way that the user can confirm the process, recreate the process, and understand how the files were actually put together. So here's an example. Seth gave a talk a few weeks ago where he went through the very technical process that goes into this. If you want to go back and listen to that, I highly recommend it. But basically, this gives you a snapshot of how we can take these two processes of 2D to 3D registration for the object I just showed you, and the computer will automatically generate all of the steps that the image went through, the order that they went through those images. Eventually, we hope to be able to make this interactive, so you can click on the box and see where the landmarks actually were on the different images that were input into the system. Several people are working on metadata schema or adding metadata tools to make our job easier. This is an example of one that goes into the details of building a 3D model. The Smithsonian has done a lot of 3D imaging of their objects, and we can take their 3D elements and use them to track the things and explain the things like Seth talked about with photogrammetry, where we track the camera positions. We can include all of that information in a metadata file that gets attached and carried along with the files as scholars use them. And then even for Stephen's work and the machine learning and AI and convolutional neural networks, that it is possible to also build and automatically collect data that will provide basically a digital roadmap, if you will, blueprint for how these really complicated black box, quote unquote, images that we are creating were made. And all of that is designed, as I said, to engender the trust of the scholar, so or the public. So back to our, I'm going to stop sharing now if I can. Back to our question about the role of the computer scientist and why it's important. There is a bit of a break of trust in a lot of institutions these days, but I think there is one between the trust in the computer scientist and the user at large. We've always just clicked the buttons and believed that whatever appeared was there and was legitimate, and we didn't have to worry about it. But as these tools become more and more into play, the computer scientist is really going to need to take seriously their ethical call and try to think ahead of how their tools could be used in a bad way, and how to reassure the public and prove to the public that the products they're getting are legitimate and authentic. So now I'm going to pass it back to Brent, who I think is still here. Yes.
Yes, I am. Thank you, Christy. I'm going to share my screen. Can you see that?
Yes.
Good. Yeah, so when I first started this work a decade and a half ago, I only had experience with medieval manuscripts, beginning with the Beowulf manuscript. And even among medieval manuscripts, it turns out that there's a very deep well of material that ends up becoming a candidate for something like virtual unwrapping. This particular manuscript from the Cathedral of Chartres outside of Paris was one of 20 that was badly damaged and burned in the bombings of World War II. An errant bomber hit the cathedral, and we managed to collect some data on one of them, and you can see the data showing you cross sections here from the tomography. You can see straight up that the writing inside this medieval manuscript is clearly visible. We use the term invisible library because it turns out that there's a ton of material out there in libraries and museums already, locked away, not under just lock and key, but under the damage that has occurred that prevents scholars from examining and understanding that material. So it might be one question that you ask as you see these kinds of tools being developed, you know, how widely distributed are they going to be able to be applied? Is there very much material out there for which this is going to matter? we've expanded as we've done this work, and you've seen from these great talks the tools that are in our toolbox, not only about applying machine learning and photogrammetry, both of which are coming of age really in just the last 5 years, but also the metadata that helps us talk about authenticity in the provenance chain. We have these tools in our toolbox now, which we didn't have before, and so there's a manifold amount of material that we've looked at before, and only now can we reevaluate. What you're seeing here is a piece of the Iliad, which we scanned under ultraviolet light before we really had a fully multispectral system. And you can see the marginalia become apparent in the scanning of the ultraviolet light. We also have examples from other medieval manuscripts that we scanned in the past, which we can now go back and put into a form that fully realizes all the things over the past decade and a half we've been working on. But I want to close out with a quick tour of a couple things that we'd love to be able to work on. This fragment in the Dead Sea Scroll collection in Jerusalem at the Israel Antiquities Authority is thought to be part of the Ezekiel scroll. And there are a lot of layers inside this fragment. It's the size of the palm of your hand, found in one of the caves at Qumran, completely unanalyzed. You can imagine how we'd love to be able to take a look at that in some detail. There are actually modern materials that await. For example, this original written by hand Jack London manuscript with editorial comments as well, thought to be safely stored away in a safety lockbox in a bank, but it happened to be that that bank was in the path of an earthquake in San Francisco that caused a fire, and that fire carbonized the manuscript that was inside that box, leaving it now completely unable to be opened. Here's a sheaf of papers from the Franklin expedition. Searching for the Northwest Passage, Franklin and all his crew were lost without a trace, and for a long time nothing was known other than this small sheaf of papers and some clothing from one cadaver that was discovered by the first search party 2 years later that went out to find them. Since then, much more has been found by way of artifact, but no written material. Mummy cartonnage. Ancient world was full of cartonnage that has since been diffused throughout the world. And I want to point to the Morgan 910, another early medieval manuscript that is completely unable to be opened, but we are actively working on it as you saw. And I wanted to show you an example of what the internal pages actually look like. So this is what we're dealing with from the Morgan 910. This is an early copy of the Acts of the Apostles written in Coptic, and you can see the text is clearly visible, but we'd love to be able to render this as if we were able to take a photograph. And finally, I'll point to recent work at the Israel Antiquities Authority, where there are many, many fragments the size of the palm of your hand or a fingernail that consist of many layers, and they remain unanalyzed. It's a big puzzle, and when you can't see what's on the layers because they can't be taken apart, it's a puzzle that cannot be completed without something like virtual unwrapping. So if you take a look at some of our recent work, here's a rendering that shows Hebrew, likely Hebrew. Scholars say it could be Aramaic because the letter forms overlap, and because these are fragmentary, we don't see complete words. But those surfaces and the ink on those surfaces come completely from virtual unwrapping and the ability to see inside using tomography and the tools that you've heard about today. And I'll finish by saying we have not forgot about Herculaneum. And so the many fragments, hard actually to count how many fully intact scrolls there are from Herculaneum. Authenticity of these unquestioned. They were excavated and protected, so the provenance chain is certain to be from the ancient world. It's potentially a cache of written material unlike anything we've ever seen. Possibly virtual unwrapping is the thing that can bring it out. So as I finish, I'd just like to thank my really talented team for their effort, and thank you all for listening.
Well, thank you very much, all of you, for a fascinating presentation. And I'm sure we'll hear more about this project as it continues over the next years. We are out of time, so if you have questions, feel free to email them to members of this group. Hopefully the recording of this will be available. And if you presenters want to send me slide decks, I'll be glad to put them up at the webpage for keeping current. So see you all in the spring. February 3rd, we already have some talks signed up for then. See you then. Bye.